Good afternoon, good morning, good evening, everyone. Welcome to Eliis Technical Forum. We are delighted to have you on board today. I'm Emmanuel Bodia, Product Marketing Manager, and I will be your host for today. Before diving into the agenda, I would like to say a few words about the Livestorm platform that we are using today. That's the Livestorm, that's the platform we're using for this event. So if you look at your right-hand side, you can see a window, and at the bottom of the window, you have a couple of tabs. You have a chat tab and questions tab. That's the two tabs we're going to use today. In the chat tab, feel free to write anything that you'd like to write, say hello, or report an issue while connecting. And speaking of connecting, if you're using, if to connect to Livestorm, it would be better for you to use Chrome. So if you're not using Chrome, you might have some connection issues. So please try to use Chrome as much as possible. And then you have the second tab, which is called questions. And that's where I encourage you to write your questions throughout the event. We've got a tight schedule today, so we won't be able to have Q&A sessions after each presentations. So please type in your questions here and we will answer as we go. You'll see to the left-hand side of the question, you also have a small window with an arrow where you can vote for the questions you are interested in answering or listening to the answer. Okay, so now let's have a look at the agenda for today. So we will first have a short introduction by our CEO, Benoît Matta, and our product manager, Laurent Souche. And then we'll jump into PaleoScan new features for the 2023 version. And we will develop a bit more on the main features, waveform classification tool, and the matching pursuit for spectral decomposition. After that, we have a 5 minutes break, so we can rest, stretch our legs, grab a cup of coffee, and then we will reconvene around 4:30 p.m. Paris time. And the second part of the forum will be dedicated to case studies. So the first case study will focus on site identification for wind farm implementation offshore Netherlands. The second case study will showcase PaleoScan workflows applied to CCS and with an example from the Smeaheia Fault block in the North Sea. And the last presentation of today will be given by Ronald Daniel from Stadsolier, and he will present some work he has done on Suriname Guyana Basin, and we thank you and we thanks him for presenting with us today. So with that, I wish you a wonderful event, and I hope you will enjoy it.
Thank you, Emmanuel, for this introduction, and hello, everyone. Thank you for being here with us today for our annual Tech Forum. I'm Benoît Matta, CEO of Eliis, and I'm very pleased to be with you at this event today, where you'll discover our new version of PaleoScan, PaleoScan 2023. The Eliis team and I started a new cycle at the beginning of this year, and building on great foundations, the team released the PaleoScan version that I'm pretty sure will bring you value in your day-to-day work. I must say that I'm very proud of their achievement, and I take this opportunity to thank all of our team members. Prior to let our team present you new features and case studies, I will share a couple words around what you can expect from us in the months and years to come. So 3 years from now, we aim to be a fully integrated seismic interpretation platform as a first objective. And secondly, we want to become a technology champion, enabling the energy companies meet the subsurface challenges of the energy transition. And to bring this vision to fruition, we established a couple strategic teams that we'll present right now. Okay, perfect. So notably, we want to address multi-data integration and interpretation. We also want to be interoperable and facilitate our user experience. For sure, we will leverage the power of AI to enhance our RGT model workflows. And finally, we want to advance towards better seismic reservoir characterization. But we also want to make a strong footprint in new energies in the years to come. And for that, we already have you covered with some case studies, specifically around CCUS and wind farm that will be presented to you later on today. So right now, I'll let you with Laurent Souche, our product manager, who will get into further details with our product roadmap. Thank you, everyone. And Laurent, you can go on.
Thank you, Benoit. So I will be presenting today briefly what is our roadmap for the next versions of PaleoScan for the next couple of years, and what are the orientations that we are taking in terms of development and in terms of research. So in terms of short-term and mid-term objectives, we want to implement the strategic map that Benoit has presented using the 3 pillars that you see on this slide. The first pillar is about completing the exploration workflow and producing all the results that you need to put on a report or in a presentation to take exploration decisions. For example, should we drill this prospect or not? And in that respect, we have identified 2 elements which we need to work on. The first one is producing professional quality maps with all the information you need and with a proper design. And that will be our first focus. We will also work on uncertainties, structural uncertainty in particular, and on being able to compute probability of success, for example, and compute probabilistic volumes, P10, P50, P90 volumes, for example. The second pillar is about reservoir modeling and reservoir development, and it consists in bridging the gap between the qualitative interpretation that we traditionally do in PaleoScan, where we are able to produce very convincing stratal slices showing all the geobodies, and what we need for building a reservoir model, which is often a probability of facies, for example. So that second element is really all about integrating well data with seismic data. And to do that, we are going to improve some of the tools that are already in PaleoScan, like the crossplot, and develop new tools to facilitate this integration. And the third pillar is about technology. And technology means 2 things. The first thing is leveraging all the new technology that is around artificial intelligence in PaleoScan in the model grid workflow that's consuming outputs from artificial intelligence, but also using machine learning algorithms to build better model grids. And the second element is about integrating better in the new exploration and production ecosystem, and that means connecting with SDU, for example, or being able to read directly and write directly VDS seismic files. So if we decompose this roadmap in 3 years, we'll first focus on mapping uncertainties, direct native VDS capabilities, and getting the platform, the architecture of PaleoScan ready for artificial intelligence and 4D. And I will detail a little bit later what it means. In 2025, we are going to focus heavily on integrating well data and seismic data, and for example, in terms of properties and producing precious probabilities, etc. We'll also have a revamp of the PaleoScan user interface to have better user experience and to make it easier for people coming from another application to get used to PaleoScan. In 2026, we'll focus on faults, managing thousands of faults easily, semi-automatically, but having the ability to edit the fault network and to produce a model from a set of watertight faults. We'll also work on automating workflows in PaleoScan. If I detail a little bit this roadmap, you will see that in 2024, we will work on mapping, and that means the map presentation, having nice maps with all the elements you need, but also having clean fault cuts inside the maps, all the symbology you expect to display normal faults, reverse faults, and workflows to create proper maps in the first place. The second key element in the 2024 release will be the handling of VDS format natively without the need for a transcoder like FAST, and being able to produce compressed VDS. We'll also work on some UX elements, for example, the ability to design your own ribbons in PaleoScan to really customize your own workflows. In 2025, we'll have many different features that are all related to better integrating well data with seismic data to identify geobodies, produce probability of fishes, and extract as much information as possible from the seismic. And that will imply some revamp of the way we handle wells and logs currently in PaleoScan. In 2026, as I already mentioned, it's all about fault modeling, creating watertight fault frameworks that include large number of faults, and being able to repeat a workflow, a PaleoScan workflow automatically when the interpretation has changed or when the input data has changed. On top of these main projects, we will get sure that whatever we develop can be used for CO2 storage workflows. So, for example, all the uncertainty work we'll do will get sure that we can apply it to the screening of CO2 storage sites and the risking of the storage sites. The 4D work we'll do will be applicable to CO2 storage monitoring, and the work that we are going to do on faults, we want to apply it to the creation of mechanical models for also assessing the risk associated with CO2 storage. Aside from the mainstream developments, we have multi-year research projects that will also in the end be released as commercial deliverables. And the first one is the Open Model Grid project. In this project, what we want to do is to improve, enhance the model grid construction, which is currently in PaleoScan, by allowing multiple input attributes. You will be able to use multiple attributes to constrain the model grid to build a better model grid, and multiple scale to build this model grid. What it will enable is the use of attributes coming from artificial intelligence, for example, to help building the model grid. And we also want to make it to have a supervised version of the model grid where you can use an existing limited interpretation to tell the model grid how it should connect patches together. The second research project is about artificial intelligence and high performance computing workflows. So what we want to do is to be able to run processes that require heavy calculation on a separate server and then bring back the results into PaleoScan so that we can continue the PaleoScan workflow. The first release that we'll have of this technology will be about automated fault interpretation using artificial intelligence, but then we can develop and implement other algorithms that will run on a remote machine and will bring back the result into PaleoScan. Now, if we look at what's coming this year, basically, we will first have a release of the Petrel data connector for version 2023. That's really nearly there. Then we'll release a hotfix that fixes the main identified issues of version 23.1, and that will be end of this month. And then during year 2024, we'll have two beta versions. The first one focusing on getting complete workflows. We want to get sure that we don't forget any piece of the workflow so that it's easy to use the new features that we are developing. The second beta will be focusing on quality. We'll get sure that we can actually use it on any kind of input data. And we will release the 2024 version of PaleoScan in June. So that's an overview of the roadmap. And now you will see what's been done in version 2023.
Thank you very much, Laurent and Benoit, for this information about the future of PaleoScan in the coming years. And speaking of new features, let's have a look at the PaleoScan 2023 new features. This one has been released on the 1st of August this year. And I'm going to call Matthew on stage to present that.
So hello everyone, good morning, good afternoon. So I'm Mathieu Botz, I'm sales associate at Eliis in charge of Europe and Africa, and today I will present you the new features of the 2023 release. So as Emmanuel said, this release has occurred beginning of August, and I will present you the new feature. So just let me share my screen. Okay. And here are the new feature presentation. So obviously our development team and the product team at Eliis has worked very hard over the past months to deliver the best version possible. So we have improved the overall performance of the application, and we have also fixed a couple of bugs. But the idea today is not to focus too much on that. The idea is more to focus on the main 4 new features that we have in the software.
Sorry to interrupt you. I can see a blank slide. I don't see your slides. So, and I think people cannot see your slides.
Okay, sorry. I will stop sharing.
You try again, maybe.
Yeah. Just let me know if it's okay now.
It's coming. Yes, for me it's okay now, but it's not in a slide mode. Now it's in slide mode. Perfect.
Okay.
Thank you.
Thank you. Sorry for that.
No worries.
So the idea is to focus on the main new features that we release in the PaleoScan 2023 version. So we have a couple of improvements. So I will talk about the improvement on the 2D and 3D model grid, because it's really the earth of the PaleoScan technology. So we try version after version, years after years, to improve the functionalities about the model grid. We have also improved and reshaped the user guidance to help our users to gain some autonomy using the software, also to flatten the learning curve using the software. We have a new method for the classification, which is called the Waveform Classification. And we have also a new method, a new algorithm for the spectral decomposition. So the spectral decomposition already exists in PaleoScan, but we have a new algorithm, which is called the matching pursuit algorithm. And this presentation will be given by our R&D manager, Fabien Cubisol, just after. And just a quick comment about the Petrel link. So as Laurent said, the Petrel link for Petrel 2023 will be available mid-September, so just in a couple of days from now. So regarding the improvement, we have some improvement on the model grid computation and on the model grid constraint. So if you are familiar with PaleoScan, we have reshaped a bit the interface to compute the model grid. So we have organized the different settings and the different parameters into different tabs. So we have one tab for the model grid parameters, okay, which is almost the same than the previous one. And we have now a tab for the structural and stratigraphic constraint where you can input your fault and your horizons. I will come back to that just after. And one tab for the model grid extent. So to compute the model grid only in a small vertical extent between two horizons or between Z limits, okay, to reduce the size of your grid, and also include some extrusion zones using 3D object, multi-Z object, layers, or geobodies. So regarding the horizon constraint, if you are familiar with PaleoScan and you have already used some external horizon as constraint in the model grid, you know that the horizons are a kind of soft constraint. So it means that when you compute your model grid, first you compute your model grid and then you use these horizons as constraint. So PaleoScan will not change the position of the nodes. It will only use the horizons to connect the nodes following your horizon. So it's a kind of soft constraint, but your model grid is always signal driven because you are tracking the polarity of your seismic. So this method is still available in the software. Okay, we haven't removed this method, but we have a new method that you can use while creating the model grid. You can input one horizon or couple of horizons. The horizon can be an external horizons, okay, picked out of PaleoScan, an horizon coming from the model, another model grid, or from an horizon stack. Okay, it doesn't matter. If it's an horizon object into PaleoScan, you can use it as a constraint. And PaleoScan, in this case, will use the horizons as a hard constraint. So it will modify the position of the nodes, so create some nodes that will follow your horizons and connect these nodes to follow the horizon. So if I show you on a real example, so at the left-hand side, you have the classical way, okay, the previous way to compute the model grid. So here we are only using the signal, okay, the seismic amplitudes. PaleoScan will automatically track the different polarities, okay, based on the parameters that you have set up, peak, trough, zero crossing, inflection points, also the patch size, okay. So here it's only signal driven, and at the right hand side, okay, we have exactly the same data, the same input parameters, okay. The only difference between the two models is that for this we have input while creating the model grid an external horizons to constrain the grid. And you can see that in this case PaleoScan will modify the position of the nodes, okay, and connect your nodes following your horizons. So the two methods with hard constraint and soft constraint will still exist in the software, okay, depending what you want to do and the confidence that you have in your horizons, okay, you can use one method or another method. Obviously, if you have a low confidence in your horizons, you have to be careful with this new method. Otherwise, you will introduce some error in the model grid. So maybe it's better to first compute the model grid, which is signal driven, and then use your horizons as external constraint. And obviously it's working for 2D, but also 3D model grid. We have also some improvement on the 2D model grid creation regarding the extrusion zones. So previously the extrusion zones already exist for 2D model grid creation, but you can only input 2D objects, okay? So layer, geobodies, or multi-Z object. It was not possible to use 3D objects, so now it is possible to use also 3D object, even if you are computing the model grid on 2D lines, okay? So that's the improvement that we have set up for this new version. Regarding the 2D workflow, we have also a couple of improvements. Okay, so the first one is a new computation method, okay, a new metric to compare the different mini traces to increase the patches connection. So this new method is called cosine similarity. And if you compare the old metric and the new metric that we have in the software, normally the new metric will search for more connectivity, okay, because it will look for 2 pixels instead of 1 to improve the connectivity between the patches. So what does it mean in terms of results? So you will have more connectivity in your model grid. So if you have more connectivity, you have less isolated patches, and it will be also easier for you to reconnect manually than the different patches. So the manual parts of the interpretation will be lower. Okay, so the interpretation can be also faster. So the idea is really to help the user to save time during the interpretation process. Obviously, if you compare the two results, okay, the two results will not be completely different. Okay, we just increase a bit the connectivity between the two methods. And last improvement on the 2D workflow. So if you have already used the 2D workflow, okay, it is not working exactly the same than the 3D workflow. And especially for the preview and for the full signal-based geomodel. So with the 3D method, you can directly compute a preview when you create your model grid. Then you are able to directly display a preview and compute a geomodel which is fully automatic. Previously with the 2D, it was not possible. Now you have the possibility to have a preview which is only signal based. Okay, so you don't need to mark a couple of horizons to have access to this preview. And it's the same for the geomodel. You can input your line set, okay, compute the model grid on your line set, and directly be able to compute a full automatic geomodel. Obviously, the result that you will get, and especially the accuracy of your model, will depend the quality of your data and the complexity of your data. But it can give you directly, very quickly, in just a few hours, okay, a preview or a first geo model to scan your data, and then you are still able to refine manually, okay, your model. Regarding the user guidance, we have also a couple of improvements on the user guidance. So the user guidance is still available in the upper toolbar using the question mark. Okay, so for the guidance, okay, we have improved the user experience for the guidance. So the window can pop out of the PaleoScan workspace. So if you have two screens, you can display PaleoScan on one screen and the guidance on the other screen. We have a couple of chapters, okay, to find the right topic that you want to address in the user guidance. And you have also at the top the search bar to search by keyword, okay, depending what you are searching in the user guide. We have also embedded some resources in PaleoScan. So if you are familiar with our YouTube channel, you know that we have a couple of videos about tutorials, tips and tricks, new feature, etc. On our website. The idea here is to embed directly the videos into PaleoScan, okay, to have access quickly to these videos to guide the users. Okay, and our marketing team is also working also with the help of the different geos based all around the world to work on more videos for the future to also increase the autonomy and the guidance to our users. And we have a third table, okay, where we have embedded the questions and answer. So again, to guide the users. Obviously, the idea is not to replace or to remove our support. The support line is still available for all our users, and you can contact directly by phone or by email our support team, and the support team is still willing to help you and very happy to help you if you have any questions about PaleoScan and the different functionalities of the software. And last improvement on the guidance, we have a new window, which is called Infobox window, which is by default at the left-hand side of the application. And this new window, when you move your cursor on the different buttons, on the different tools of PaleoScan, you have a small description in this info box of the action related to the tools. So if you want to know for new users or for new workflow or new tools that you are not using on a regular basis, what are the action related to this button? Okay, you can have access very quickly to the action related to this option. Okay, so again, to guide our users in the different workflow and tools available in the software. Another improvement, so we have a new method for classification, which is called Waveform Classification. So just a quick comment about the availability of this new classification. It is not part of the core package, okay? It is part of the properties modeling add-on, okay? So maybe some of you don't have access to this package, okay? So no worry, if you want to test it, you can contact your local sales, your local representative on the different Eliis offices and ask for a trial license if you want to test this new feature, which is not part of the core package. Okay, so no worries, and really don't hesitate if you want to test it. So what is this waveform classification method? So the waveform classification method is a classification method based on some automatic pattern recognition that we apply on the seismic waveforms. And the idea is to gather a portion of seismic traces which have the same frequency, phase, and amplitude. Okay. So why we are doing that? We are doing that because it's quite useful to highlight some variation in stratigraphy, lithology, fluid contents, and also bed thickness. So the workflow that we apply in PaleoScan is a three-step classical workflow, and this workflow is quite automatic. You will see it just after during the live demo. So the first step is the definition of the input data. So obviously we want to extract some waveforms, so we have to input a seismic volume, and the extraction of the waveforms is performed along an horizon. So you need also to input an horizon. So again, the horizon can come from the model grid, external horizons, horizon manually picked in PaleoScan, or an horizons extracted from an horizon. Okay, it doesn't matter. So you will extract your waveforms, and in the second step, you will use the extracted waveforms, okay, along your horizons, and use it as an input for a clustering algorithm. So the clustering algorithm that we use here is the self-organizing map method. Okay, so it's the same method, one of the two methods that we also use in the cross-pattern classification already available in the software. And the output of this method will be the different classes, the different templates that we can create. Okay, so this template we can go up to 9 classes. So here I only display 4, but we can go up to 9 classes. And then the idea is to compare the extractive waveforms with the different templates, okay, and assign, okay, the waveform to the class which is similar in terms of amplitude, frequency, and phase to create the classification. So that's the classical workflow that we are doing. So to go a bit more in details, how it works. So first we will perform the data extraction. So the two inputs that we have to define is the volume and the horizons. The extraction of the waveform will be along a vertical window, okay, following your selected horizons. And this window can be symmetric, okay, so same number of sample above and below the horizons, or asymmetric. You can set up these parameters, okay, so you can choose if it's asymmetric or not. And you will extract your waveform, so you will end up with your set of waveforms. This set of waveforms will be used as an input of the clustering algorithm. So this step is a bit automatic in the software. Okay, so the extracted waveform will be used as input in the self-organizing map methods to create the different templates. Okay, so the different templates, the automatic class templates, we can go up to 9 classes into PaleoScan, will be automatically generated. And then the last step is the classification itself. Okay, so we will compare the real data, so the waveforms extracted along the horizon, with the different classes, okay, that we have generated from the clustering algorithm. So here, for question of legibility, I only display 3 classes, but the software will compare the 9 classes and will assign, okay, the classes which has the maximum correlation. Okay, and we can do that for all the waveforms extracted along the horizons to create our classification map. You have also the possibility, so to use obviously the automatic template, but what you can do is to extract the waveform along an horizon. Okay, so at well location, along a well, using a well. So you can use, instead of the automatic classes, you can use the waveform extracted at well. And in this case, you will have the 8 automatic classes plus the waveform extracted at 12, which correspond to the class number 9. Okay, and PaleoScan will recompute the classification, taking into account this new class. Obviously, the classification will be a bit different, not totally different, because you can replace only one class by the waveform extracted at well location, but the classification can be a bit different using this method and taking into account real data instead of automatic classification. So I will switch to the live demo directly into PaleoScan to show you how it works. So if you want to have access to the waveform classification, you have to activate your property modeling. So again, if you don't have access to this, don't hesitate to contact your key contact at Eliis, okay, and we can give you a demo license if you want to test it. The waveform classification is available in the Horizon toolbar, so you have a new button available at the right-hand side of the application, okay, of the toolbar, and you will open a new window for the waveform classification. So the first step of the waveform is the definition of the input. Okay, so first you will select your horizons, okay, for the extraction along your horizons. The second input is the seismic, okay, to extract the waveforms. You can also use for the vertical display. So here you can see that you have the vertical display behind. Okay, so by default, it's the inline and crossline of your 3D volume. But if you want to display vertically your classification, you can also use a 2D arbitrary line. It's an option, okay? So if you don't put anything here, okay, it will be only the inline and crossline of your volume. Here you have the parameters that you can set up for the window size, okay? So you can, it's in number of sample, and you can choose a window which is symmetric or asymmetric, depending the data that you have. And then you can start your classification. So PaleoScan will extract along your horizons your waveforms. Then it will use the clustering algorithm to create the classes and create the classification map. Okay? So it just takes a few seconds here to compute the classification. So here we have our 9 classes. Okay, so very quickly, you can check or uncheck the box to display the different classes. Okay, you can also preview the classification on a vertical section. Here you are in a blending viewer, so you can change the transparency, okay, if you want to display more your seismic or your classification. Here you have your classification map, your probability map, I will come back to that just after, and the attribute viewer, which is the extraction of the seismic amplitude along your horizons. So here you can see your different classes, so the different color correspond to the different classes, and you have the possibility to merge some, to hide some classes, and also to merge some classes. So for example, here I can see that I can see one channel, okay, here, and I have the possibility to merge, for example, class 9 and class 2 if I want. So to do that, I can go there, okay, to see my different classes. So I can see that my class 1 is hidden, okay, but I can just show it again. I can select the class 2, okay, to merge it with class 9. Okay. And PaleoScan will recompute the classification using these two classes which has been merged. Okay, so you will have instead of having 9 classes, you can have 8 classes, and you can merge like all the classes. You have also the possibility to display the probability map. Okay, so by default, the probability map that you display is the maximum probability, okay, at each waveform location, so along your horizons. So here it's a kind of confidence map about your classification. So you can see the area where you have high confidence in your classification and the area where the confidence in your classification will be lower. And you have also the possibility to display the probability map for each individual class. Okay, so here I choose class 2. So PaleoScan will recompute the classification map only, the probability map, sorry, only for class 2. And here I have access to the probability for class 2. Obviously, if you are going to blue, the color scale is here. So the blue is low probability. And if you are going to yellow or orange or red, the maximum probability will increase. And last option that you can perform is to replace, okay, the wavelet at well location. Okay, so you can select in your project folder any wells that you want to use to extract the waveform at well location. Okay, and you can replace any classes. So you can select the class that you want to replace, and if you want, you can also reset. Okay, in this case, PaleoScan will recompute the automatic classes and will remove, okay, the extractive waveform at well location. And the two outputs that you can generate from this classification, okay, there is two possible outputs. Obviously, it's the classification map that you can save. So you will save an horizons with a new attribute on it. okay, which is the classification, so a discrete attribute from 1 to 9. And you have also the probability to save the current probability map, okay, so the one that is displayed. So if you are doing that, so here you can see that it's the maximum probability. But if you want to save the probability, for example, for class 2, you just have to change on the display, and then you are able to save this probability map for class 2. Okay. So that's the different output that you can generate from that. So that's all for the presentation of the waveform classification. And the last improvement, the last new feature that we have in the 2023 version is the spectral decomposition with a new algorithm, which is called matching pursuit. So previously, we already have short time Fourier transform and continuous wavelet, which is already available, and they are still available, so you can still use it. And we have a new algorithm, and the window is still the same. So you input your horizons, you can compute in real time your spectrogram, selecting your different method, and preview the result of your spectral decomposition. But for this part, I will let my colleague Fabien Cubizol, R&D manager at Eliis, present the matching pursuit method.
Thank you, Mathieu. So I'm going to share my screen. Okay. So hello, everyone. My name is Fabien Cubizol. I'm a R&D geoscience manager at Eliis, and I will present the new algorithm for spectral decomposition, which is the matching pursuit for PaleoScan 2023. So what is the aim of the matching pursuit algorithm is to decompose a seismic trace into a series of wavelets. So we start from an original trace, and then we try to estimate the wavelet that compose the trace. And then the sum of wavelets will be able to reconstruct the initial trace. So it is an iterative process. And the first step will be to focus on the maximum of energy of a seismic trace, maximum energy event, and then trying to estimate the wavelet that correspond to this event. So we'll try to find the frequency content, the phase, its amplitude, etc. And then once we have estimated this wavelet, we can remove it from the initial trace and then focus on the other, the next maximum event with the event with the maximum of energy, and doing the same process. So we can remove it and then go to the third one, etc., etc., until obtaining a trace that has no more interesting information from the seismic data. So we can assume that it corresponds to residuals, and then we stop the iterative process and then go on to another trace. Thanks to all these wavelets that we have defined, we are able to construct the spectrogram corresponding to the seismic trace. So the first viewer here corresponds to the seismic data with the selected seismic trace, and then we can compare here different spectrograms from the algorithms that are available in PaleoScan. So the first one corresponds to the matching pursuit algorithm, so the new algorithm available here. And if we compare it with the wavelet transform wavelet transform algorithm from the Morley wavelet and Ricoeur wavelet, and also with the Fourier transform with the parameters of window size, we can see that the resolution of the spectrum is way better thanks to the matching pursuit in terms of time, but also in frequency term. Then, if we want to see the results along a line, specific frequency, we can compare here the matching pursuit with a wavelet transform. We can clearly see the difference between the two results in terms of time and vertical resolution. We can see that the matching pursuit is way better concerning the vertical resolution of a specific event. So when do we apply the wavelet transform and Fourier transform, and when do we apply matching pursuit algorithm, they all have their own pros and cons concerning the algorithm. For the Fourier transform and the wavelet transform, it's a very great algorithm because there are fast processes which gives beautiful results. So it's perfect for creating maps on regional data, for example, but it has a bad time frequency resolution, especially compared with the matching pursuit. So we will use the Fourier transform and the wavelet transform if we want to study regional cases and reconnaissance of this data. It's also used to identify gross geological features. For the matching pursuit, it has a very good vertical frequency resolution, but it's also time consuming because of its iterative process until getting a residual final trace. And it's also very sensible to noise because of this estimation of a maximum of energy. So we will more use the matching pursuit for reservoir analysis and also to identify subtle depositional changes, and of course to have an accurate vertical localization of specific events. So the tool of spectral decomposition in PaleoScan is available from the volume toolbar. So you will still be able to create Fourier transform and wavelet transform spectral decomposition. But now you have a new option for matching pursuit and its specific parameters. The parameters of the matching pursuit are the scale, minimum and maximum of the wavelet that will be created to estimate to be removed from the initial trace. So this scale, actually, in order to understand this parameter, corresponds to the number of side lobes of the wavelet. So for example, here we have an example of scale factor about 1.2. So it means that we have more than one side lobe next to the main center of the wavelet. And here we have an example of scale factor of 2.5. So you can see that we have two side lobes surrounding the center wavelet. So it's just to try to help you to understand this parameter. And of course, we also have the threshold parameter, which is a percentage of the initial trace in order to say to the algorithm, okay, from this, for example, here, 20% of residual as this threshold, I consider that all the rest of my seismic trace is not interesting, and I consider as noise. And here we have an example of spectrograms using different scale parameters for the wavelet. And of course, if we select a high threshold, you will only focus on maximum energy events on the wavelet. So you have less information on the spectrogram and then less information on your decomposed frequency line. And if you use a lower threshold, the process will be more time consuming, of course, because it will go on the iterative process, but you will have more information on your spectrogram and final result. So here we have the global interface of spectral decomposition. So you still have to enter your input seismic volume that is displayed here. Thanks to the cross navigation, you will be able to select the seismic trace that you want to use to display to create the spectrogram, and then click on this button to be able to select the peak frequency that is displayed in the final viewer. Okay, and then you will be able to save 1, 2, 3 or more frequency volume and being able to display them on a RGB blending viewer, for example. So let's go to a quick live demo. Okay. So Here we have PaleoScan 2023. So the tool is available from the volume toolbar, which is here, Spectral Decomposition. So I click on it. And for this example, I will use my data, which is a great seismic data with a lot of geological features, such as channels. So I can display here an horizon stack with RMS amplitudes along this seismic. So this horizon stack has been created thanks to the model grid of PaleoScan. And then we will focus on a specific channel, which is here, this one. Okay. So we'll try to highlight this channel thanks to the spectral decomposition using matching pursuit. So as an input, I select the seismic volume, which is displayed in this viewer. And thanks to this cross navigation, I will directly go to the event. The seismic event is here, representing the channel that we want to highlight. Okay. You can see that the spectrogram is updated in real time. So this event is here on the spectrogram. Okay, like this. I can zoom in and zoom out as I want. Here, for now, the spectrogram is computed from the Fourier transform, so I can change the window size in order to change the resolution of the spectrogram. I can select a new another algorithm, which is the wavelet transform, for example. And also I can select the new algorithm available in 2023, which is the matching pursuit. So here we have the spectrogram computed from the matching pursuit. We can change the parameters, which are the scale of the wavelet, minimum and maximum scales. And we will be able to see the changes directly in real time on the spectrogram, like this. Okay. And we can also select the threshold parameter in order to define the threshold of the residuals. So if we select a high value, for example, 0.5, the computation of the spectrogram will be very quick, and the computation of the matching pursuit will be very quick because it will focus only on the major events of the seismic trace. But we will lose a lot of information between these particular events. Okay. And if we select a lower value for the threshold, of course, the iterative process will be longer, but we will have more information along the seismic trace. And then, of course, on the final frequency decomposed volumes. So, for example, I will use a threshold of 0.2, and I will select a frequency which is at the peak of this seismic event, which is around here. So I just double click on this step, and we decompose the volume at 52 Hertz, like this. Okay, and here we have the results in real time of this decomposed data. So compared to the wavelet transform and Fourier transform, because of its time-consuming process, we only focus on traces around the selected one. But you still be able to change, for example, for 0.3 and see the results in preview in this tab. Okay. You can also, of course, change and move the selected frequency here. You can add other one by picking on it, just like the previous tool that we have in previous version of PaleoScan. Once you have picked one or two or three or more frequencies, you can click on save and compute the different volumes corresponding to each frequency. So once you have created all the volumes, you can map the results on Horizon Stack and display the results in a RGB color blending view. Okay. So I just drag and drop the matching pursuit for 3 different frequencies that have been selected in order to highlight the channel that we want to work on. And then of course you can navigate through the different horizons of the horizon stack, and finally see the results of the spectral decomposition, seeing great channels, and finally see the one that we want to focus on, which were here. Okay. If I go here, we can here be able to see the results on this viewer. Sorry, just a lag. Yes, perfect. Like this. Okay. And if you want to see the resolution, the vertical resolution of the channel thanks to the seismic data, you can navigate through the horizon stack, and you can see here the intersection with this yellow line, and you can see that the time resolution of the spectral decomposition from Matchable Suite is better than Wavelet Transform, for example, if you want to compare them together. So this is the end of this presentation. Thank you for listening. And Emmanuel, you can take the lead. Thank you very much.
Thank you very much, Fabien. It was very nice. Thank you to you and to Mathieu for this very great overview of those main features that are now available in PaleoScan 2023. So feel free to try them on. Don't hesitate to post your questions or on the tab, or to send us to us afterwards. And should you need any more details or a demo, we'll be happy to help with that. We're going to start the second part of our technical forum, and this one is dedicated to case studies. So we are a bit running out of time now, so we will start straight away with Benjamin's presentation on site identification for wind farm implementation offshore Netherlands. Benjamin, the floor is yours.
Thank you, Emmanuel. So I hope you can see my screen. Just let me know if you
Yes,
can't.
I can see it.
Perfect. So good morning, everyone. Good afternoon. Good evening. So my name is Benjamin Duro. I'm a senior staff geoscientist working at Eliis. And today, like Emmanuel said, I'm going to talk about a case study that we've conducted offshore Netherlands. So the data is called 10 Northern Vanden and London Wind Farm Zone. And so actually this is a data ultra high resolution seismic that has been acquired for wind farm site characterization. So basically, why did we choose to go with this kind of data is because so far, when it comes to the oil and gas industry, we don't play, I mean, we play with high resolution seismic, but not ultra high resolution seismic. And in the wind farm industry, they do have a lot of ultra high resolution seismic. And so far, we didn't know how PaleoScan would behave and if PaleoScan was able to handle such kind of data. So this is why we wanted to give it a try. And because we had some really nice results, we just wanted to let you guys know what we came with. So actually here, I won't teach you anything basically, but the aim of the offshore wind farm is obviously to convert wind energy into electricity using wind turbines. And then once the electricity has been created, then the idea is just to convey this electricity on land using subsea cables. So that's why we have to make sure that the site is safe enough and all the infrastructure won't be damaged by anything. So when it comes to the offshore wind farm industry, we have a lot of pros and cons. So the main pros actually is that the wind is considered as inexhaustible source of energy. So this is truly a renewable energy. Then the location of the offshore wind farm is most of the time away from the local population. So the distance actually creates or cancels all the worries about the site and the noise, because obviously no one wants to have a wind turbine in his garden, right? So it also reduces the impact on the local environments. So it spares land for farming and house building, for instance. Obviously, there was also more space available offshore because 70% of the globe is covered with water. And if we compare similar installation on land and offshore, the wind is most of the time stronger and more consistent offshore. So if we compare similar installation, the offshore installation will give, in average, 60% more of energy. Of course, there are some cons. So the main one is we still have to assess the impact on the birds and the marine life. So some studies are ongoing. And it is obviously more expensive and more difficult to install and maintain such farms. So again, that's why we have to make sure that all of these infrastructure are safe enough. So the data actually is located offshore Netherlands. So you can see here the extent of the 2D data. So it is composed of 153 square kilometers of 2D data. And within this area, we do have a smaller area made of 3D data. So it represents here only 6 square kilometers. So this is fairly tiny. And actually, this location here hasn't been chosen randomly. It is adjacent to the Gemini wind farm zone, and that has been up and running for the past couple of years now. And so the site investigation here has been located there. Okay, so this is 56 kilometers northwest of the Schiermonnikoog Island, which is just right here. So actually, unlike the oil and gas industry, where actually we want to focus quite deep in the subsurface, because we want to know, obviously, the source work, and we want to know the history of the basin. When it comes to the wind farm site characterization, only the few hundred meters matters. And in the North Sea, the sediments are in such trench here. The sediments are dated from the Quaternary era. So I will just spare you the entire geological context, and I will just focus on this. So when it comes to the Quaternary sediments, actually the Pleistocene epoch is marked by 3 major glaciations. So the first one is known as the Elsterian episode. So this one occurred between 500,000 to 315,000 years ago. Okay, so you can see the extent in red here. So the ice sheet went fairly south in the UK, okay, but not as south in the northwestern Europe. Then actually the second glacial episode is known as the Salian one, the Salian episode. So this one occurred between 300,000 years ago to roughly 130,000 years ago. You can see the extent in yellow. So it was a little bit less extensive in the UK, but a little bit more in the northwestern Europe. So you can see that these 2 glaciations here have a direct impact on the site, okay, because it is lying just underneath the ice sheet at that age. And the third episode is known as the Westphalian glacial episode, also known as the last glacial maximum. And so this one occurred between 115,000 years ago to roughly 1,200,000 years ago. And so this one, actually, you can see the extent. It wasn't as great as the 2 previous ones. So it didn't have a huge impact on the site. But actually, later on, during the Holocene period, the temperature increased. Okay, so this was due to changes in the Earth orbital eccentricity and inclination. And so because of this increase in temperature, well, the ice sheet started to melt, and then we had a major transgression. Okay, so the entire North Sea was then filled with siliciclastic sediments. So actually, PaleoScan is fairly known in the oil and gas industry now because we can deal with a lot amount of data. We can have decent results. But actually, when it comes to the wind farm industry, the data and especially the resolution is much higher. So actually, that's why we wanted to know if PaleoScan was able to handle such data. So for the ones who don't know PaleoScan yet, actually, so I will just give here a quick sum up. So the idea is to bring in data, okay, so seismic, horizons, faults, wells. In my case here, I just started with a seismic. And then the application is going to create what is called a model grid. So this is a sub-volume composed of millions of nodes. And then the application is going to link all the nodes together to create the horizons. And our job as geoscientists is to QC what PaleoScan is producing. And so actually, once we're quite confident with the interpretation, the next step is to derive what is called a geomodel or a relative geological time model. And thanks to this geomodel, we can then extract numerous horizons or surfaces. So they're called horizon stacks. And these horizon stacks are just a pile of surfaces. And then we can just map any kind of attributes. And this allow us to scan what is within the data. And so, of course, we can analyze and interpret the data. So here is the segue that I have imported. So actually, the format was exactly the same as what we used to see in the oil and gas industry. So it was encoded in 32 bits, floating points. The only thing that changes is the bin size. You can say the bin size is 50 centimeters by 50 centimeters by 1 meter. So even if the area is fairly small or reduced, only 6 square kilometers, the size of the data was 200 gigs. Just to compare with the data that we have in the oil and gas industry, most of the time we'll deal with data which is about 25 meters by 25 meters and 4 milliseconds, for instance. And when we are lucky, we're dealing with 12.5 meters by 1.5 meters. So here, the resolution of the data is really ultra high, and therefore the density of the lines is also really high. And so that's why even if the area is fairly reduced, the data is massive. And again, we don't go as deep as in the oil and gas industry because we basically focus between 0 and 200 milliseconds. So I was able to load the data, so it just took 1 or 2 hours, so that it was fairly quick. Then I was able to create the model grid. So again, it was fairly nice. For the model grid in here, actually, because I only had a reduced amount of time ahead of me, actually I had to decimate the grid. Okay, so instead of working on the full high resolution, I decided to decimate by 2. So then the bin size dropped down to 1 meter by 1 meter by 2 milliseconds, and actually the size also was divided by 8. So the size dropped down to 25 gigs. So all the computations went faster, and also the navigation was a bit easier. So PaleoScan was able to create the nodes. Because we had the nodes, PaleoScan was able to create the automatic interpretation. So that was perfect. It took a couple of hours. And so then actually I was able to QC this interpretation. So I was able to mark the horizon. So in here, all the horizons are product consistent. And once I've done so it took me about 5 or 6 days. And so then I was able to derive the relative geological time model, or the RGT. And in here, all the patches are chronostratigraphically sorted. Okay, and thanks to the continuous layers, we can then extract an unlimited number of horizons or surfaces. So I did compare these surfaces to the seismic data just to make sure that we didn't have explicit discrepancies. Of course, so far they did look okay. So that's why actually I could move on to the next step. That was the interpretation of the data. And actually I was able to map some attributes. So in the top right corner here, we can take a look at the seismic itself. Okay, the orange line here represents the horizon that I'm currently looking at. So the top left corner here represents the Z value, okay, in milliseconds. The bottom left corner here represents the root mean square attributes that has been calculated over a vertical window size of 5 milliseconds centered on the horizon. And in the bottom right corner, we can take a look at the spec D, okay, that has been computed based on 3 remarkable frequencies. So the first one, the low frequency, is 199 hertz. The middle frequency is 442 hertz, and the high frequency is 729 hertz. So by the way, you can also see here that, first of all, the density of the lines is much higher, but also the frequency content is much higher. And again, here, we didn't know what to expect because the frequency content goes from 0 hertz to 5,000 hertz. Okay, so just to give you an idea, in the oil and gas industry, we go from 0 to 100 or 150 hertz. Okay, so here we go until 5,000 hertz. And actually, so this is really high, and this is because we don't have to go as deep as in the oil and gas industry. Okay, we can just focus on the few hundred meters, so we can use a much higher frequencies. So on the seafloor here, actually, we were a bit disappointed because we wanted to see a lot of things, wrecks or cables or boulders, for instance, but we didn't see any because only things that we could see was the footprints acquisition. So we were a bit disappointed, but actually this leaves room for improvements, and we are already thinking about some improvements that I will just name at the end of the presentation. So then if we just keep going down a bit, so you can see here we're just below the seafloor. So we can see some anomalies here and there. So we can clearly see them in the RMS and also on the RGB. So from the literature, actually, and I did ask my peer, we didn't know for sure what it was, but it could be actually a barrier island, okay? And we can see here a channel-like system, kind of. So if you do have a better idea, please let me know. Then if we just keep going deeper, and this is when it becomes to start being very interesting. So if we keep going deeper, actually we can see here this incision here. So it is clearly visible on the z-value map and on the others as well. And this feature actually can look like a channel, but its morphology is not quite common, okay, compared to what we used to see in the oil and gas industry. But the thing is, keep in mind that at that time, we were in a glacial episode, okay, so it means that we had a very thick ice sheet lying on top of the sediments. And actually, because of this ice sheet, so when we are in a glacial episode, it means that the static level goes down. For instance, during this Salian episode, the static level dropped down to about 130 meters. And there is a dewatering process around the glacier where the glacier flows from the top to the glacier to the bottom. And water actually flows down, so on top, in the middle, but also below the glacier. So this is not at the sub watering process. And so actually, when the water flows down, this dewatering process erodes the sediments as well. And so these incisions here are known as tunnel valleys. Okay, so that's why the shape can be a bit irregular. And what is important here for the site characterization is that down the tunnel valleys, we should expect to have some outwash fans. Because in here, we might find boulders and other features that can damage, for instance, the cables or the turbines, or the pile of the turbines, actually. And if we just drop a lightning on top of it, actually, we can clearly see here this path here. So this could be an old outwash fan here that we can see. So this could be an area where we should spend more time focusing the data. So far in here, so we didn't see any boulders also, so this is kind of safe. But from the literature, we know that we have some boulders just down here. Then actually, if we just keep going deeper, so we can still clearly see the incision here, here, and there. We can also see some features here on the RMS and also in a SPECD. So these ones are also tunnel valleys, but they are less incisive. Okay, so that's why they're not really highlighted in here with the interpretation. But actually what I want to focus on right now are these features here. So they're not quite visible, but I will just zoom in so you can just better take a look at them. And these features here are looks like deformation of a rigid sediment, actually. And again, we have to keep in mind that we were still in a glacial episode. Okay, so we had a thick ice sheet on top of overlaying on top of the sediment. And actually, when the ice sheet moves forward, because of its weight, the sediments are kind of bulldozed in front of the glacier, and this results in some sort of thrusting deformation. So what we can see here, what we can clearly see here, are actually linked to glaciotectonic processes. So it is clearly visible in here and there. And actually, again, if we just keep going deeper, again, we can still clearly see this incision here, which is the tunnel valley again. And if we look actually at the SPECD, so it's not quite obvious in here on the RMS, but on the SPECD, we can see that we have a very clear blue anomaly. So this anomaly answers very well to the high frequency content. So if we just zoom in on it, we can also see something on a z-value. And if we take a look at the seismic, we can see here a package of continuous seismic reflections, okay, that are lying horizontally. And actually, we can see this seam form here. So this formation here doesn't look like the previous one, okay, because the sediments are not chaotically deformed, or we don't have this kind of thrusting effect. But actually, again, if we think about glacial episode, we also have to think about interglacial episodes. And the thing is, when the temperature increases, of course, the glacier is melting, so the glacier backs off, and it leaves behind it some block of dead ice, some massive block of dead ice, and the sediments are being deposited around this block of ice and on top of it as well. And at some points, when the block of dead ice melts, the sediments will collapse, and this will create a lake. And so this lake here is known as the Kettle Lake. Okay, so this is a sign of a massive block of dead ice. And so again, this is fairly important for the site characterization because this could be quite hazardous. And so just to conclude actually with this, so of course the wind farm industry plays a major role in the energy transition because the wind, of course, is inexhaustible. We have a lot of available space offshore, and also the distance from the local population cancels all the worries about sites and the noise, and it gives also more power compared to similar infrastructure on land. We've seen that obviously thanks to the right algorithm, thanks to the right workflows and tools, we can quickly assess what is lying on the seafloor and just below the seafloor. So for the site characterization, actually, this is really important. And this idea has been completed only in 2 weeks' time. So it can go actually very quick. And of course, like I mentioned in a couple of slides, on the seabed, we could see only the acquisition footprints. So we are only thinking about new improvements, such as being able to import multi-beam echo sounder images, for instance, or side scan sonar images, for instance, that we can just drop on top of the seafloor to really see what is within the data. So actually, I would like to thank the Netherlands Enterprise Agency for providing me the data and all the reports actually written by MMT, Arcadis, and Geoengineering. And on behalf of Eliis, I would like to thank you for your time and attention. And with that, Manu, the floor is yours.
Thank you very much, Benjamin, for your nice presentation. It's quite interesting to see how PaleoScan can be used for near-surface challenges as well. So very interesting. Thank you.
Thank you.
Now we're going to jump into the next presentation. We will show you how PaleoScan workflows can be applied to carbon sequestration with an example from the North Sea in a Smeaheia Fault block. So I will call Sven Philip for this presentation. Thank you.
Hey, Emmanuel. Hello, everyone. So thank you for being around. So I'll now share my screen so that you can all see what we're going to be discussing about. There we go. So the presentation I will have will be made of a few slides for the introduction, and then quite quickly we're going to jump into PaleoScan to just see how concretely we've been running our case studies of the Smeaheia area, like Emmanuel was mentioning. So for the context, of course, we all know like the CO2 contributes to global warming. We've got to decrease the emission, but we also have to store in geological formation the CO2 from wherever we're producing it. And in this particular context, well, the Norwegian government have been committed for a long time to store and to run pilot studies to store the CO2 into the storage, into the natural storages. So among these many studies and envisioned plan of storage, we have in the map here the Aurora field that is in the North Sea offshore Norway, just west of the famous Troll oil field and gas field in this case, sorry. And you see in this map that there is a pipeline that is planned from the coast from natural gas pipeline to well 3157. And what we notice is that in this area, we also have like a specific area that we call the Smeaheia area, which is in the Horder platform located between two major faults, which are the Øygarden fault complex to the east and the Vetter fault on here. And we've got some seismic blocks, in particular, the one I'm circling now, available in these areas, and we also have some wells available. So these locations would, of course, represent more storage opportunities. So because the data is public, we wanted to give it a try at the exploration, the appraisal workflow we could run with PaleoScan. In terms of context, of geological context, you've got the seismic section that is linking the two wells you see here. So you've got the west to the left of the image here, and the east to the right side here. The color that you see in overlay on the seismic section highlights the geological edges, right, from the Triassic on the top of the basement down there to younger sediments. And in particular, the reservoir formations that are targeted for these potential CO2 storage are the Jurassic Sternifjord, Fensfjord, and Crossfjord formation, which are capped by a regionally known cap, which is the Dropner formation at the base of the Cretaceous. So this is for the context. So now again, the question is like, how can PaleoScan participate to the CCS storage appraisal? So this is what we cover in these case studies. Just as a reminder, this is the typical workflow that we could follow in PaleoScan, and the step I want to show you in PaleoScan, so directly today, are these steps where we derive a horizon stack. We're playing mapping in the horizon stack to analyze the potential environment of deposition of the reservoir and the vicinity of the reservoir we're targeting. And later on, in a later stage, we also want to see how to create a gross rock volume after having converted these time volume into depth. So this is the data you're about to see in a moment. So basically, we're starting with seismic data, a couple of wells, in particular the two that are intersecting the currently displayed section. There are a few faults that we've also interpreted here, okay, that are structurally compartmentalizing. We're going to see our reservoirs. This is just for the recap. You all know, like most of you may know, like how PaleoScan is quickly getting from the seismic information to consistent geological model that you see here to the right. We're building a grid, and actually how are we automatizing our process is that we're connecting all the nodes of the grid essentially based on the similarity of the seismic amplitude. So this is just for the recap. And now, with this method, this is the type of geomodel that we are obtaining in the Smeaheia area. So you recognize here the previous section I was showing you, now in co-rendering with our geomodel on top. So you can see that the geomodel is nicely capturing the geometry of the geology behind. And on top of it, we're going to use the available velocity logs, interval velocities in this case, just to derive some a simplified velocity model. That is going to be necessary to depth convert our data and consider some dimensions laterally and vertically that are going to be consistently in terms of distance. A few assumptions that we're obliged to make here to eventually compute some gross rock volumes. The first assumption is that both the Vetter fault and the Östergarden fault involves enough clay smear to be to consist of barriers that would prevent leakage across the faults. Also, that the Dropner formation on top is thick enough to avoid any breach, any leakage throughout the cap itself. Okay, in this situation, and the reservoirs are at least 800 meters in depth. So at these depths, the gas would be supercritical, so will not induce super overpressure on the cap. And that's approximately. Then we've got different scenarios with some gas column that we want to try. Before I jump into PaleoScan, I just want to thank Gasnova Equinor for providing the seismic data necessary for these case studies, and also the Norwegian Petroleum Directorate, NPD, for providing the well data. And Jonathan Chin down there is our intern from last year that also helped creating this project. Right, so let's jump into PaleoScan. So here we are in the interface of PaleoScan. You see again the data we're using for this case study. You can see the coast of Norway in the background in black, the rear. And now I'm going to use the sessions just to more quickly get to the step where we analyze the environment of deposition based on the mapping we've created on horizon stacks. Okay, so what do we have here? So I'm going to start with the bottom viewer. Here in the bottom viewer, you've got a vertical section of the seismic. And again, just so that you can locate yourself in the stratigraphy, you've got this color code that tells you about the age of the geological age of the sediments. And then on top, you've got two horizon stack viewers with two different mappings. The one I'm moving right now to the left is a mapping, RGB blending mapping with different frequencies derived from spectral decomposition. And the horizon stack to the left is to the right, sorry, has a RMS amplitude mapping, right? So strictly the same surface, but two different mappings so that we can compare what we have. Again, keep in mind that the reservoirs that we're looking for are inside the Jurassic. So what I'm going to do, I'm going to start scrolling and scanning through these horizon stack at the base, from the base of the reservoir, so a little bit at the top of the Triassic. What we can see here, by the way, is that we can recognize some fluvial systems that are continental fluvial system, which is consistent with the literature that is depicting this kind of system in the Triassic. Then if I'm moving up, so I'm just going to synchronize these two horizons. Yeah, here we are. So that we can move up into the basis of the first of our reservoir. So I'm just moving up a bit. And here we can recognize some specific features. So here these sort of tidal flats, with a drainage system that we can interpret as a drainage system, get all the features in there. Then we are going to move up into what we are assuming would be the reservoirs. And if we're looking quite closely, we could analyze coming from the east some fairways or some alluvial fan deposits here and there. It's more visible with the RMS amplitude this time. I keep scrolling up, see some of these features that are aligned like from the east to the west. Okay, maybe another one here. See this lobate structure to the northeast over here. So this is consistent with a silicoclastic and porous sedimentation for these stratigraphic levels. Okay, and I'm just going to move a bit faster now, so you recognize some other features like this if you're looking closely. Just to go to enter the cap. Okay, so the Dropner formation in the lower Cretaceous, where, well, nothing is actually exciting. It's quite homogeneous, and actually it's rather good news to have a homogeneous cap over here, a homogeneous seal, right? It's consistent with the absence of breaching in this location. So this is the kind of scanning just to appraise the environment of deposition and just check if it makes sense with the regional literature that we have at hand. And then now in the next step, we're going to jump into depth domain. So just so that you can be aware of this, I'm going to restore another session here. Very quickly. You know what I'm going to do here? I'm just going to show you how we're performing this time depth conversion. So first, what you have on top, you've got a blending with different features. So you've got the seismic that we have here, and then we're building a geomodel, like I showed in the slide, with depicting the geometry of the sediment. And then based on the velocity logs, we can create our velocity model. So this is eventually the velocity model. It's a volume. And then we're going to use this volume to depth convert the data. Okay, so I'm just going to perform this just in front of your eyes. So right now I'm inputting a seismic volume, which is initially in time associated to the velocity volume you see on top. Okay, I can adjust a bit the size of the data, the type of display, and then dynamically I can switch the data, from time to depth and back and forth. And in this case, precisely because we want to compute the crosswalk volume of the reservoirs, then we also need to convert, in particular, the horizons corresponding to the top and the bottom of the formation. So we have the horizon in time here, and they can also be converted, according to the same velocity model. We can also convert the faults. Okay, I didn't input any faults right now, but these are the essential items we need to convert in depth in this case. So let me jump into the depth domain. All right, so here you've got three viewers. So on the viewer to the top left, sorry, you recognize the three subformations that are likely to be our reservoirs. So you've got also from the top, maybe the Dropner formation in black. And then in dotted formation, kind of a yellowish, you've got at the top, the Smeaheia formation, then the Fansfjord formation and Crossfjord formation at the bottom. You see that there is a slight disruption between the top Smeaheia and then the next formation beneath. On the gamma ray logs, we see a bit of shale content in there, so we're not sure they are super connected. So there are different scenarios to run about this. And you recognize these formations as being displayed in depth in the 3D environment here, okay, with the same color code. So what we have to do if we want to now compute a gross rock volume, we have to consider the top of the formation we want to analyze. Okay, we have to do this theoretically one formation at a time. So once for the Smeaheia, once for the Crossfjord, and once for the Fansfjord. This one is the top of the Smeaheia. And what we're going to do, we're going to play with a specific threshold tool here, okay, to just mention what would be the top, the shallowest point of the trap. So shallowest point here would be at 800 meters. So I'm just going to adjust one end member of my value at around at 800 meters here. And then for the spill point, depending on the scenario we want to pick up, we can adjust different scenarios. See if you are very pessimistic to control the spill point intersected by our volume, we could just limit ourselves to something like 970 meters. But let's say we're more optimistic and say like there is no like lower spill point just outside of the block. See, like we can increase a bit the depth of the spill point like this. Okay, I'm just giving you like a random example in here. The next, we have to pick up a piece, like a piece of these Brute threshold that we want to consider inside our trap. So I'm doing this now. And then we're going to use the GRV, the gross rock volume tool that is here. So you see here in this interface, we still have the topmost piece of the trap. We also have the spill point, which is the NZ. And because for the Smeaheia formation, I told you it was probably disconnected from the other pieces of reservoir, I'm also going to have to indicate as a base for the reservoir, well, the base of the Smeaheia formation itself. You see, I've got plenty of horizon in here, and I'm going to use the bottom parts, the bottom of the Smeaheia, the base of the Smeaheia formation. I'll readjust the stepping so that you have a more precise a more precise sampling. Okay, and here we have a table that is showing you the area versus depth. Okay, so you can, by the way, change the units if you want to make them a bit more, not consistent, but corresponding to bigger units. So I've changed it to kilometer, like square kilometer, cubic kilometers. And then you've got of course, the depth dimension vertically and the area along the horizontal axis. And what we want to focus on here, because there are like three curves, three different colors, is the green curve. Okay, the green curve is the evolution of the area available inside the trap as a function of the depth. So you see that it will increase until a certain point, like around 1,000 meters, and then it decreases because now we're catching the bottom of the Smeaheia Fault formation itself. So this area will reduce. We could express the same thing in terms of volume versus depth. Okay, we're still interested by the green curve here. And of course, now that we have these curves, we can export them and compare them to different scenarios. So for example, different level of spill point, etc. So now to materialize the different scenarios that we've been running, I want to show you one last session, okay, where we can see all the traps that we've been considering. So here we go. So you still have the same reservoir formations in transparency here. Okay, they're not super visible, but they're in transparency. And we're looking at the data from the north. And you see actually that there will be two different traps in the areas in this Smeaheia area. There will be one trap here in the structural high to the north of the volume, constrained by a fault that will be the Veta fault to the west. Okay, with a certain extent. See that it's no more spread because there is a leaking point here where the gas or the brine would leak up towards the east. And here on this other side, you have the second piece of the trap, so which is often called in the literature the beta trap. And you can see for all of the three reservoir formations, so the Smeaheia Fjord, Fensfjord, and Crossfjord, the three different traps materialize here as geobodies. Okay, so you've got in level of pink, the three traps in the three different reservoirs. And ultimately, what is quite convenient in PaleoScan is that you can, of course, compare. We can export these volumes, and you can also, of course, compare the volumetrics directly inside PaleoScan. So if you want to display the alpha trap, for example, that would be this one. You can change again to cubic kilometers. Yes. Okay. And I could also show the beta trap, okay, in a quite optimistic case where spill point would be down to 1,100 meters for each of the three formation, F for Fensfjord, K for Crossfjord, and S for Smeaheia Fjord, and you could compare the volumes. All right, I'm coming to the end of my workflow now and what I wanted to show you. So I want to thank you for your interest, and don't hesitate. If you've got some question, I'll have a look into the chat.
Thank you very much, Sven. It was very instructive to see the PaleoScan workflow applied to carbon or to CO2 storage. So very good. Thank you very much.
Pleasure.
And many thanks to you all for participating, asking questions, and joining us today. So with that, I wish you a wonderful day or a wonderful evening, wherever you are in the world. And let's keep in touch. Goodbye.